So just let me briefly introduce David. David got his PhD 2006 in Princeton. With his advisor was Nathan Seiberg. The title of his thesis was Non-SUSY Aspects of Field Theory and String Theory. So he worked on more formal questions also. He did postdocs at Harvard and at the Institute of Advanced Studies in Princeton. And since 2009, he's a faculty member at Rutgers. Going a little bit away from his thesis topic, he also worked on supersymmetric topics, in particular quite a bit on gauge mediation, various aspects. And since 2009, he's been working also regularly on long-lived particles, or extensively on long-lived particles, and so also on more phenomenological topics. And more recently, and that's what the subjects of these lectures are about, he's been very interested in deep learning and machine learning and the applications to colliders and how it can help us look for new physics. And as I said, that's what he wants to talk to us about today. And so thank you very much, David, for agreeing to do this and taking the time. And please go ahead.
Okay, well, yeah, thanks for the opportunity. I was happy to do it. I recently just finished giving a semester-long course here at Rutgers on the same topic. So it's not too much work for me. It is sort of a challenge to condense 26 hour-long lectures into four 2-hour-long lectures. But I'll try to do my best to give you at least a flavor of things. I should also announce, I guess, that it's kind of a last-minute addition, but I'm gonna just offer like office hours of some kind in case people have any questions and the lecture time isn't enough. I'm happy to answer any questions. And so I guess somebody will send around a link to a different Zoom link for my account so that I can open it. And that'll be, at least today, we'll try that out after the lecture. So 1 hour after the lecture. So that'll be 6 o'clock your time. Okay. So, yeah, and so let me just get started. Can you all, am I still sharing my screen? Yeah, so can you all see this? See me writing? So,
oops. Yeah, okay, yes, now I see, yeah, deep learning, yeah, okay.
Okay, great. All right, so the topic of these lectures are going to be deep learning applications to LHC. And so I'm not going to assume you've encountered deep learning or machine learning before, so I'm going to introduce the basic concepts of that, and then I'm going to talk about the applications to the LHC. So I'm sure you've all seen in the news, in recent years, there's been a deep learning revolution happening in say the real world, and we've seen breakthroughs due to artificial intelligence and deep learning happen with things like image recognition, image generation, right? Natural language processing, which usually refers to text, also speech recognition, game playing, and the list goes on. So all these amazing successes of the last just the last 5 years or so. It's quite breathtaking. And of course, this has everybody excited in various fields. And it's fair to say, I think, that this revolution is coming to our field, high energy physics, and the LHC, and many other fields. And generally, the places where deep learning can have a big impact are places where there's a lot of data. So a lot of data with complex correlations, high dimensional. So data which is not easy to understand or not possible to understand using conventional methods alone. So places where the data is itself, an object for sort of a terra incognita for study. These are places where deep learning is having a big impact. And so obviously the LHC is one of the sort of epitomes of big data. And so deep learning is having a big impact there. Okay, so that's what, so that's what I'll be trying to share with you in these lectures. And so more specifically, so the purpose of these 4 lectures, or the theme, maybe I should say theme of this course is, I think, applied AI. Okay, that is, there's going to be a, there's going to be a focus on the applications, okay? And so not too much theory, which would mean like, not too much statistics, just barely enough to explain things, proving things, and I don't know what else, machine learning theory, I guess, ML theory. I think there is a whole field of study, which is theoretical machine learning. And it's very interesting, but that's not what this course is going to be about. Okay, so instead it's going to be primarily about the application. Okay, so you're going to be exposed to, I'm going to try to explain, most of the modern deep learning algorithms. So that includes, DNNs, CNNs, maybe RNNs. Maybe, I'm not sure there'll be time. I'll show you what GANs are, generative adversarial networks, autoencoders, normalizing flows. So all of these are sort of state-of-the-art, or the beginning of state-of-the-art algorithms or architectures for doing different things with the data, different types of data. Okay, so we'll have an introduction to all these algorithms. We'll also discuss core ML concepts. So that includes, different levels of supervision, like unsupervised learning, weakly supervised learning, etc. So different tasks, like classification, regression, etc. So the concepts like the maximum likelihood, some statistical concepts, I guess you could say, that will be part of the course. So the maximum, in this lecture, we'll already talk about maximum likelihood, the Neyman-Pearson lemma, and then finally, we'll talk about neural network training. So that's things like stochastic gradient descent, overfitting, things like that. Okay, and I guess, yeah, so finally, we'll also be talking about, so after all that, or in each lecture after this one, I'll be introducing LHC applications. So that'll be jet tagging, things like calorimeter simulation, calorimeter, and searches for new physics. Okay, and so that's actually the organization of the lectures. So today is going to be about ML basics and neural network basics. I'll see how much I can get through of that. And then this will be, we'll spend lecture 1 on classifiers and their application to boosted jet tagging at the LHC. Lecture 2, oh, sorry, lecture 1 is today. Lecture 2 is tomorrow. Lecture 3 is about generative modeling. And lecture 4 on Friday will be about anomaly detection. Okay, so that's the plan of the course. And let me just say, please interrupt me often with questions. I'm going to put 2 underlines under that one. So this, especially being the Zoom era, everybody has their camera off. I have no idea if anybody's listening, and I get rather discouraged after a while. So please interrupt me with questions. Don't be shy. And that'll also help me, gauge my speed. And I'm sure if you have a question about something, somebody else in the audience does too. So you'll be doing everybody a favor. Okay, so
hey, let me just briefly. So just unmute yourself and ask your question. I think if it gets too much, then we'll do a raise hand. But that would be a luxury to get there to too many questions.
Yeah, feel free to just interrupt. I think, yeah, unless that turns out to be burdensome, but I think there's, the number of people in the course are not so many that will be a problem. Okay, and so I think the plan for every day is there's 2 hours allotted, and I'm gonna give people a 20-minute break in the middle. So I guess that means, yeah, I'll lecture for 50 minutes. You guys can have a 20-minute coffee break, and then we'll reconvene after that. Okay. So any questions so far about, the topics or the format or anything? Okay. So let me get started. So what is machine learning? Maybe I should take a quick poll just to get the level of the audience, because I haven't met any of you guys. What is your experience so far with machine learning? Have you? I can only ask yes or no questions, I guess. Have you studied it at all before? If you have, you can raise your hands. Oh, there's even an X. Okay, good. How do I see? Let's see, participants.
So 8 people, 9, 10, 11 people have raised their hands so that they've heard of it before. 3, 4 have an X, meaning probably no knowledge.
Okay, so
15 we're up to 15 for positive response.
Okay, thanks. Yeah, great. So I'd say the majority of the course has seen it before. How many of you are actively working on it for your research? $11 people are actively working on it for their research. Or 8. Okay. So a fair number of you are actively working on it for your research too. All right. Okay, thanks. So yeah, so let's see. well, you guys can give me feedback after the first lecture if it's going too slowly. And then maybe for those of you who have seen it before, this will just fill in some gaps in your knowledge. But okay, so, and for everybody else, I hope that, it's, I'm starting at a low enough level that you'll be able to keep up. Otherwise, you got to stop me with good questions. Okay, great. So what is machine learning? So that's what I'm going to start with. So, you may have heard about this fancy thing, machine learning. It's doing all this amazing stuff. But all it is really, I'm going to say in a nutshell, is it's glorified. Oops, can I spell? Glorified curve fitting. I think that's all we're doing to first approximation, is we're doing glorified curve fitting. But okay, but it's not so trivial, right?
Would you say that that's broadly or just when it's used in particle physics?
No, broadly.
Okay.
Okay, but you may think of curve fitting as like spline interpolation, least squares regression, but this takes it to a whole nother level, right? So this is fitting functions with millions. I think in the natural language world, so this is not in particle physics, but in like Google or something, they've reached billions of parameters to enormous data sets. And here, enormous, if I can't spell enormous, here enormous means both many data points. Usually it means many data points and many features per data point. So that's an important distinction that we're going to come back to over and over again. So it's good to not be confused about this from the outset. For example, here's an example. So millions of images, these are the data points. So each image is like a data instance, right? And with, say, 1,000 by 1,000 pixels each. So these are the data points, and these are the features, right? So the data here is enormous, right? We have a lot of information, and we're fitting it to functions with unprecedented number of parameters. So that's why deep learning is successful, and that's why it's non-trivial. And yeah, so the question I think everyone should have, if told this, is how is this possible? How can we manage to get any satisfactory fit to the data with such crazy sounding functions? And that's what the algorithms and things that I'm going to tell you about accomplish. Okay. So that's the new element here with deep learning. And once we've fit these functions, so with a fitted function can do many things. In general, that means, well, actually that's just so the main thing that we can do, I think all the tasks I'm going to describe are of this class. So if you have a fitted function fitted to the data, what is the main thing you want to do with it? You want to, you want to interpolate it, right? So you can do many things, and I think they all are you can all think of, I'm going to tell you what the tasks are in a moment, but I think you can think of them all as some form of interpolation, That is, if I've fit a function, say, to these data points, right? Like that, then I can, you know, if I'm given now a new set of data points, I guess, let's see, if I'm given a new set of X values, so these are the X and Y values. Oops. If I'm giving a new set of X and Y values, sorry, if I'm given a new set of X values, then I can use my function to predict what the Y values would be, right? Even though the function hasn't been trained on those X values. If they sort of come from the same statistical distribution that describes, sorry, probably, I don't know if you can see my cursor, but even if they come from the same statistical distribution, can you see this cursor now?
Yes.
Yes.
Yeah, okay, great. So even if they come from the same statistical distribution as the black points, then the correctly fitted function will give me the correct Y values for these red points. Okay, so
just to ask something obvious here.
yeah,
so you're saying that then machine learning is some sort of a, you know, in rough terms, an interpolation black box, and the harder problem of extrapolation is probably something that it cannot grapple with. Would that be fair to say?
Yeah, so that's the next excellent question. Yeah, so the next, you know, yeah. So in order to do extrapolation, it would have had to actually learn the underlying, you know, think about this. What I drew here, ended up drawing here, is like a cubic or something, right? So to do extrapolation, it would have had to learn that this is a cubic, and then it could extrapolate it, right? But given just the data we have, I think you cannot conclude without some additional prior, let's say, that it has to be a cubic. It could always be a cubic plus tiny corrections that only blow up, you know, outside this range, right? So yeah, extrapolation requires actually understanding what's going on at the underlying level. And in general, this is not something deep learning, or all these things that I described earlier, attempts to do. There are, I guess, attempts to do that, but that's not what I'm going to talk about, and I'm not sure how successful those are. But yeah, so this is interpolation, and extrapolation is much harder and requires a deeper understanding than just fitting to the data. Okay, but you know, I don't think we should undersell interpolation. It is still, as you'll see, can do many amazing things to have a function that interpolates between your data points really well. So we'll see that over and over again, what that can do for us. Good. Did that answer your question?
Yeah, thank you.
Mm-hmm. Say another way, if we could really extrapolate with neural networks, then, well, maybe we can, because some people are getting rich off of this, like on the stock market or something. So, but very few people are getting rich that way. So it's not so easy, I think. Okay. Good. So, right. So, all right. So with the fitted function, do many things that are all, I think, types of interpolation. And so now let me talk about categories of ML tasks, things that we can do with this fitted function. Okay, so the first one that comes to mind is probably, for most people, although I don't know if you're familiar with the terminology, is regression, right? So that's what I just showed on the previous slide. So this is regression. So regression is basically, so we have the input data, X, and we have the outputs Y. These are called the target, or output, or labels, a lot of names for y, okay? And the thing that makes this sort of conventional regression is that y are continuous. Okay, so the labels are continuous labels, then it's regression, okay? And then we try to fit a function to this data, and the fit function is of the form f of x, and also depends on some parameters, w. So these are the fit parameters, or in neural networks, they're called weights. Well, weights and biases. Okay, so that's probably the kind of function fitting we're all most familiar with, which is regression, right? So you can think of it as a special case of regression, but the next, and this is actually the single most popular or common ML task, would be classification. Okay, so classification is just regression. You could think of it as regression with discrete labels, right? So, so maybe your right. So how should I draw this? Right. So I have two labels. Let's say I have, for example, let's say I have two labels, y equals 0 and y equals 0 and y equals 1, right? And for y equals 0, I guess the x, I have to tell you what x looks like. Maybe for y equals 1, x looks like this. This is the actual data that I'm fitting to. And for y equals 0, x looks like this, right? So then I could fit a function to that, which just looks like this, right? If I knew how to fit a function to that looks like that, I would have a perfect classifier, right? That would be my fitted function. But in general, x is not just one dimensional. So another way you'll see this plotted that's perhaps more practical is say I have two x's, two-dimensional x's, and say that all my class 0, so y equals 0, all at class A live here, and all my y equals 1 points, y equals 1 points, class B live here, right? Then then what I want is to draw a boundary between these points like that. This is called the decision boundary. So it's another way to think of the binary classifier. It's trying to draw a separation between the two classes of points in the input space. Okay, so that's two ways to look at classification. In general, classification is regression with discrete labels. Okay, and then what does the fit function mean in this? So I drew two cases here. I drew two cases here where where the data was perfectly separable into the two classes. But a more common instance, it's never that easy, right? A more common instance is where the two classes are overlapping, right? So in that case, we won't be able to perfectly separate them. And the best we'll be able to do is to get the answer to what is the probability that a given point x came from class A or class B, has label 0 or label 1, right? So in this case, the fit function should tell us the probability that x came from class A or has label 1. Maybe I should write that instead.
Isn't that formally the same as regression? Because that's a continuous function again, right? Between 0 and 1.
Yes, yes. Well, no. Oh, good. Thank you. Thank you for the question. So, so the distinction is that the labels are continuous or discrete. The function we fit to it in general is going to be continuous, yes, or piecewise continuous at least. So the function, the fitting function is going to be continuous, but the labels are either continuous or discrete. So that's the distinction.
Oh, but we want to get out the probability now, right? And the probability is continuous.
Yes. Yeah. Oh, you mean why aren't we fitting to the? Yeah. Well, I think I'm going to explain this in more detail later. But the probability is the best you can do, but every data point still has a label, discrete or continuous. That's sort of immutable. So even though the data points could overlap, each data point that you're handed has a label, which is 0 or 1.
Okay, thanks.
Yeah, so that's ultimately what you're trying to fit to. And then the best you can do, as I'll explain later, that's the Neyman-Pearson lemma, the best you can do is to get this probability out. Yeah, I mean, if you were handed not the labels, the discrete labels, but the probability function itself, well, I guess you wouldn't have to fit anything to it because you'd have it. But if there was some way for somebody to hand it to, I guess, yeah, if somebody could hand you instances of that probability label, right? So not the function itself, but just like instances of it for all the different x's, then you could try to fit a function to that. And that would be regression again. So that, I guess that's the distinction. Yeah. Okay, good. What else did I want to say about classification and regression? Right, so I think that's about it. Oh, sorry, so fit function, probability that x has label 1. Actually, I should upgrade this to, that would be all you need. That would be a complete description of the story if it's binary classification. But if it's multi-class classification, then there's more than 2 labels. And so this probability, I have to consider the probability that it has label A, where A runs over all the labels, or all the labels but 1. All right. So, okay, so these 2 are examples of supervised machine learning, okay, supervised ML, which means training. So training is another word for fitting, okay? So fitting or training with labels or labeled data. So so if all my data comes with labels, like this Y or the class label, then I'm doing what's called supervised ML. And so you can think about where you would have applications like that. So in the real world, say with image classification, one of the first ML breakthroughs was image classification, or one of the first deep learning breakthroughs was image classification. And so there are these data sets, for instance, MNIST is all the handwritten digits between 0 and 9, right? And there's like 80,000 little images of handwritten digits that people collected somewhere. I forget where. I think NIST is the National Institute for Standards and Technology in the US. So they took, a long time ago, they made these images of handwritten digits and saved them. So that's easy. But somebody had to go through and label all those images 0 through 9 to begin with, right? And so the labels have to be created by somebody. And then a much more complicated version of that is the ImageNet database, which has like 1 million images with 1,000 different categories. Boats, planes, different types of planes, flowers, animals, all sorts of categories. And again, humans had to go and label those images one by one. And I think the early pioneers of the ImageNet database had in mind computer vision. That's why they were doing it. I think they were professors at U of I, the University of Illinois, and they needed like undergrads, and also there's this Amazon Mechanical Turk service. I think they they needed volunteers basically, or paid, people paid a small amount of money to go and label all these images. So yeah, so the labeling doesn't come for free, but we have to get it from the truth, some kind of truth source. So now you can think about how would you do supervised learning at the LHC, right? Like the data doesn't have any labels. So how would we do supervised learning? What does that even mean? Maybe somebody who's doing research on this could answer this question, or this is a question for the audience, just to see if you're paying attention. Anybody, how would you do supervised learning at the LHC? Where do the labels come from?
What I could think of would be simulations, and with simulations we have all the data.
Very good. So yeah, so if you're doing research on this, you probably know the answer. But yeah, so that's exactly right. So with the LHC, the labels are, so LHC, the labels are coming from, typically coming from simulations. So with simulations, I can make, boom, I can make QCD events or TT bar or, W plus jets, ... So I can produce events whose identities are specified in advance. And these could be the labels. It depends on what I'm trying to do, but these are often what we want for labels. I can create new physics processes. Good. So anything I can simulate, I can train a neural network on. And then, but then that raises so that's all great if the simulations are good, but that raises the limitation of supervised learning, right? So the simulations are never perfect, right? So whatever my machine learning algorithm learns is going to be learning something about the simulations. And then I have to worry about, has it learned something in the simulation that's not in the data? It's not, really nature, or what is the sort of systematic error I'm incurring from focusing so heavily on the simulation, et cetera, et cetera. So those are all considerations then that have to be taken into account. Okay, good. So that's just a little taste of that. I'll be saying a lot more about that. All right, what other tasks are there? So again, suppose I have, a bunch of data. I don't know, suppose I have a bunch of data distributed in some way. What else could I do with this? So another very powerful task is called density estimation. So that's learning. So maybe this is closer to what Manuel had in mind when he was asking about classification versus regression. Whoops. So learning the underlying probability density P of X that the data was drawn from. All right, so if we assume that the data represents some kind of stochastic process, and every event is IID, like not correlated with every other data point, then they were drawn from some underlying probability density P of X. And based on just the scatter of these data points, we could try to fit a probability function to these points, right? And what makes this task, not totally trivial is that whatever function we fit to it has to be a probability. Meaning what? It has to be, what are the two essential properties of a probability, of a probability density? Anybody? Probability densities have to satisfy what? I'll give you one. So probability density.
0 and 1, and should be.
Sorry, what?
Should be between 0 and 1 everywhere and integrable to 1, normalized.
Okay, the second one is
positive.
True.
So actually non-negative and normalized is enough, I guess.
Yeah, so d n x has to equal 1, and f of x has to be greater than or equal to 0 everywhere. Yeah. The total probability, if I were to, a probability if I were to like integrate it over any small region of space would have to be between 0 and 1, but the probability density does not. Yeah, but it has to integrate to 1. Okay, so that's why a density estimation is not totally trivial. The class, I have to construct a family of fitting functions that has these properties. And so people have various tricks and things that allow us to do that quite effectively, actually. And that I'll be talking about either in my 3rd or 4th lecture. Okay, what's another task? So suppose I've learned P of X, either, you can learn it either implicitly or explicitly. That may not make any sense to you right now, but we'll see how GANs, generative adversarial networks, don't actually learn P of X explicitly. That is, you'll never know what it is. The GAN won't tell you what P of X is, but it's secretly learned it implicitly under the hood if it's working. So, but suppose I have now access to P of X in some way. What can I do with that? Or what might I want to do with that? So of course I might know the probability density of every point. That's nice. But if I really have control over P of X, what's something else I could do with it? That's very interesting. Anyone have an idea?
Just to generate the
Yes. Suppose I've learned P of X, then I can sample from it. I could produce more samples from it. And this is what's called generative modeling. So I can sample from it and produce more, realistic. That's what realism means, is that it's drawn from this probability density, more realistic examples of the data. Well, I guess of the training data. Okay, and good. So that's generative modeling. And when you see like the deep fakes or the fake celebrity faces and things, that's what they're doing. They're fitting a function to the probability density of the image data. And then if they know the probability density of the image data, they can sample from it and generate more examples of it. And it's amazing that they can know the probability density well enough that the examples they produce are so realistic, right? Okay, so that's generative modeling. And the last example is, suppose my data looks like this. What does your human brain immediately, what does your biological neural network immediately do? It finds, sorry, I can't see my cursor unless I do this. It finds these 3 points, right? So that's anomaly detection, right? And this particular example is outlier detection, which is one kind of anomaly detection, right? That's like the easy case, at least easy for us. It's not so easy maybe to train a machine learning algorithm to do that. But still, outlier detection is the relatively easy case. What if my data, actually, here's a physics example. Oops. Sorry. What if my data is I'm going to represent it as a histogram, or as a count for X. What if my data looks like this? So what is your eye immediately drawn to? To this bump, right? So now this is like P of X versus X or something, right? So what your eye is drawn to is this bump, and what your eye is secretly doing is it's interpolating, it's fitting a function to the sidebands and interpolating into the bump region. And then it's saying, well, this bump looks like a feature on top of a smooth continuum, right? Our brains do this automatically, at least I think they do. So this is not outlier detection. All the data points that live here are not where P of X, the underlying P of X is 0, right? But what this is called group anomaly detection. And it's looking for overdensities. Okay, so this is actually what I think 99% of the ML literature is about, is outlier detection. And this is actually what 99% of our field is about, so group anomaly detection. Generally, we're not so lucky anymore to have new physics or anything interesting be outliers. We're generally looking for more subtle effects like overdensities. Okay, good. So that's supposed to be the last task, is anomaly detection. All right, so I've run through all the different tasks that we'll be covering in this course, and I think this sort of summarizes, or you can categorize almost every ML application out there into one of these categories. As always with categorizations, nothing is ever perfect, but this will get you a lot of the way there. I think that brings me to 50 minutes, so I promised we would take a break. Let me just pause and see if there's any questions before the break. Anybody have any questions or thoughts? Anything they want to discuss? It's always hard if we say you're going to take a break and then nobody wants to ask a question. Right?
I do have sort of a question. So you hear me, right?
Yeah, I hear you.
Okay,
it's a little
great.
bit muffled, but I hear you. Yeah.
Sorry, I'll do my best. So in this example of density estimation, so if what I understand is correct, so that the diagram includes x1 till xn, and you basically already have the probability distribution of your points, right? So I don't understand what you're estimating.
Oh, good. I'm glad that, okay, I'm glad you asked that in case that wasn't clear. So yeah, what makes this non-trivial is that you don't have the probability density of the points. All you have are the points themselves.
Right, but if you have many of them, then isn't that the same thing?
Ah, good. So let's say I just have, it depends on the dimensionality of the data. Let's say it's just one dimensional. Then if I have enough points, how can I estimate the probability density without doing anything fancy? Then your question is true. I mean, then what you're saying is true. Okay. So if I just have one dimensional set of points, then hopefully everybody knows how you would estimate the probability density in that case without doing anything fancy. Anybody? So let's say my data is just one dimensional, and I can't even plot that. I don't know. So if it's just data on a number line, and it looks like, you know, a lot of points here, just a few points here, and maybe just even fewer points here.
You could do it as a histogram.
Yes, thank you. So I would histogram the data, right? And then I would get, you know, counts like bins. I would bin the data, right? So that's a histogram, right? Okay, so if it's just one dimensional or even two dimensional, maybe three dimensional, like binning, if I have enough data, then binning the data makes sense. But this is called the curse of dimensionality. If my data is 1000 dimensional, then no amount of binning is ever going to give, no amount of data is ever going to give me a good density estimate with binning, right? It's going to become very sparse, right? So the amount of data I need scales exponentially with the dimensions, right? Okay. To get enough counts in every bin. Does that answer your question?
Right. So then I assume what you're going to do is to look for a certain combination of these dimensions that give you something non-sparse enough.
No. Well,
okay.
That maybe that's another approach. But what modern neural density estimation is I'm going to fit a neural network function to the data itself, even in 1000 dimensions, and I'm going to hope that it interpolates well.
Okay.
Yeah. Right. And magically, you know, it does in a lot of cases. It's a bit more complicated than what I just said, but yeah. So actually what I'll be telling you about are approaches that will, for instance, try to map this space to a latent space, let's say, to another space where the data follows just a multinormal Gaussian distribution. So if I can produce such a mapping, then I can be assured that I know what the probability density is in that new space. And if I know the Jacobian of that mapping, I can get back to where I was. Anyway, so yeah, it's not exactly what I was saying, but that's the spirit of it. We just try to fit a function to the data which has the proper properties of a probability. Okay, great. Any other questions or thoughts? If not, I guess we could take now a 15-minute break. Yes, so I see a question from Sebastian that
exactly.
says, yeah. So machine learning can pick up structures that you do not want it to pick up, and then how to give it extra context if necessary. Yeah, so this is the general problem of generalization. So Sebastian, are you there? Or did we lose him? Ah, I see Sebastian's in the audience. Okay.
Oh, he did just, he typed check, yeah.
Yeah, so good. So that's the general, that's the problem of generalization error or overfitting. So in all cases, if your training data does not represent your actual data in some way, or your training data was fine, but you fit a function to it that had too many parameters or something, so that you overfit through the training data points, then yeah, you will not generalize well to new data or new examples. And so one way to solve that, I'm not sure exactly what you have in mind with extra context, but one way to solve that is always to get more data, or to there's other techniques for mitigating overfitting. For instance, checking how you're doing on a third data set, like the validation set, is perhaps the most common technique for that. So I'll be talking about neural network training a bit later on. Does that answer your question? Okay.
We'll assume yes.
Okay, great. So let's see. I forgot to mention that all these examples here, you can see that they don't have labels, right? This is fitting functions to the data itself in various ways. They don't have truth labels attached to it. So all these are examples of unsupervised ML. Okay, so that's training without labels. Okay, so those are the two main types of machine learning algorithms, supervised and unsupervised. And of course, then, there's a continuum that ends up being populated between these two that I'll be talking about, like weakly supervised or semi-supervised. But these are the two sort of main classes, is you either have labels or you don't have labels. All right, great. So now let me talk about an example, maybe, and then I want to introduce the maximum likelihood estimation principle. All right, so suppose, again, our data looks like this, and we want to fit a line to it, right? So linear regression. This is just to a very basic topic. Of course, we all know what to do, but so suppose our fitting function looks like this. So the weights W are A and B, right? And we want to fit, so this is how to fit to the data. So how would you fit this function to the data? What do we learn how to do in elementary school or whatever?
Square.
The least squares regression, right? So the first thought is least squares fitting, right? So that should be your first thought, and there's nothing wrong with that. So let's say I have n data points, then, so sorry, this is x, this is y. I would do yi minus f of xi summed over all the data points, right? And what is this? This is the least squares, figure of merit. And what is it a function of? It's a function of the w's, the parameters, right? A and b. Good. And then I want to minimize this with respect to w, which means taking the derivative. So minimize L with respect to w. So set, a and b derivatives to 0. Solve for a and b. Okay, so that's how we would fit this line to data. We all know how to do that, right? But did you ever stop to wonder why that is what we do? So why is this least squares fitting justified? I mean, it seems like the natural thing to do, but why not the cube or the fourth power or the square root? Why the square?
Well, an odd power is not a good idea, right? You could largely oscillate around it and have canceling between positive and negative contributions.
Yeah.
You want to have an even power at least.
I could take the absolute value and then cube it if I wanted to.
Absolute value is also not a good idea if you're talking about derivatives.
Okay, fair enough. That will only come back to haunt you in a few measure 0 points. But yeah, okay. But yeah, why not the fourth power or the sixth power or a kosh or something? I don't know. So there's a reason, right? So the reason is that, so why this? So by the way, in machine learning terminology, this is called the loss function or the objective function. So, and that's a general property of machine learning, is that we're always trying to minimize. We have to accomplish our machine learning task, we have to translate it into minimizing some loss function, right? So we have to define a loss function whose the act of minimizing that accomplishes the task we want. Okay, so why this form of the loss function? And the reason, actually, at least I think the best reason, maybe there's other reasons, is something called the maximum likelihood estimation, or the principle of. All right, so what is that fancy sounding term? It's actually a very important thing from statistics. Again, I'm not going to have time to prove anything, but from the field of statistics, we know, I mean, they prove theorems there. We know that if you can construct this likelihood function, so the probability of the data given some model, and then maximizing L under the parameters of the model, right? We don't get to change the data, but we can tweak the parameters of the model. Maximizing this likelihood of the data given the model over the parameters of the model gives us the best estimator for model parameters. And best has a very technical and specific, mathematical definition that's where the theorems come in. And roughly speaking, you can think of it as if the data were drawn from this model with some parameters, then the maximum likelihood estimation procedure would give you a fit to those parameters that's closest to those parameters in the limit that the data is large, in limit of infinite data. Does that make sense? So it gives you the most unbiased and closest, least variance estimator of these parameters, if the data was drawn from this model. Okay, so good, and so that's the maximum likelihood principle. And then what do we have to assume about the model in order to arrive at this least squares. So for least squares, we assume the model is of the form P of, let's see, P of Y given the parameters and also the input data is of the form, let me put a squiggle here, e to the minus y minus ax plus b squared over 2, let's say. So in other words, we assume that the points here y are scattered around the true value according to some Gaussian distribution. That is an assumption that we make. That's part of the model. Given this probabilistic model for the data, then we can do then we are led to doing least squares fitting through the maximum likelihood estimation principle. That makes sense? So, if the model is this for an individual data point and all the data points are IID, then the full likelihood is, the full likelihood is the product over all the data points, like that, okay? And then if we take the logarithm of that, we get the sum over, so the negative of the logarithm of that, we get the sum over like that, times a half or whatever. Okay, so in practice, it's more practical to minimize, not maximize, but minimize the negative log likelihood. Okay, any questions about that? All right, so I want to do one more example, which is, because we're going to need it in the next lecture, which is binary classification. So this is maybe not something you've thought as much about. Maybe you've done least squares fitting before, but binary classification is maybe not something you've thought about in the same terms, but what should the loss function be under the maximum likelihood estimation? Well, again, the model is, as I said before, the thing that we're fitting, the fitting function is already a probability. The probability that x is, say, type class A. So we're going to write that as probability of A given x. So then what is the probability of the data given the model? That's the product over all the data. So for class A, we have this function f. And for the data that's class B, what should we put here instead? So I'm multiplying all the probabilities that the class A events are correctly, that's the probability that we think they're class A. What about for class B? What factor should I put here?
It is 1 minus f.
Very good. So I should put 1 minus f of x, my objective function, right? So this is xi, this is xj, right? So then this is L, and minus log L is equal to minus sum over I of A log f minus sum over J and B log 1 minus f. And this is the loss function for binary classification, and it's called binary cross entropy. And I can write this more compactly as sum over I in the data minus yi log f of xi plus 1 minus yi log 1 minus f of x. So this is the binary cross entropy. So yi is equal to 0 for B, I guess, and yi is equal to 1 for A. Then this line reduces to that line. Okay, and I guess I can give one more example. Any questions about that? I'm trying to go a little faster. Any questions about that? Feel free to slow me down. So in the next lecture, when we talk about, say, top tagging, we're going to be using this as our objective or loss function. We're going to be minimizing this across a sample of, say, top jets versus QCD jets. Okay, so I'll give one more example, which is multi-class classification. So now I'm going to say I'm going to have, so okay, so this is, so multi-class classification, the novelty, I guess, compared to binary is there isn't just one fitting function anymore. Rather, if I have, say, the NC classes, then I have, in general, NC fitting functions. So A equals 1 to NC, I have all these class probabilities. Is class A, and the sum over A from 1 to NC has to equal 1, right? So really I have NC minus 1 degrees of freedom here that I'm fitting. But in this case, if you follow the same logic, then the loss function minus log L should be the sum over class probability of class A log FA. So I have to sum from I of 1 to N over the data and A from 1 to NC. Okay, so you can check that with this constraint here, that this form reduces to this form. To this form here in the binary case. Okay, so the YAs end up, so FAs and F2 is equal to 1 minus F1, if you like. Okay, so this loss is called the categorical cross entropy. Okay. Any questions?
Is there a negative sign missing in the equation on the right-hand side?
Over here.
Yeah.
Yes. Thanks. Yeah, without the negative sign, we'd be maximizing that. With the negative sign, we want to minimize it. Yeah. Thanks. Oops. Good. So yeah, so what should f of x, the fitting function, be? All right. So before you get to neural networks, there's some other popular choices, right? So choice 1 would be what are called high-level features. And so that's just a fancy way of saying maybe you can study the data and come up with your own fitting function, right? So for instance, you know, you see this, you see that it falls on a line. Doesn't take a rocket scientist to know that I should fit this to a line. So I don't need a neural network to tell me that. And so that would be like a high level features. Just examine the data and come up with something by hand, right? So if it's binary classification and I'm being asked to draw a decision boundary, and my data looks like this, then what should my high level feature be to tell me what my decision boundary? It should probably be, so this is another example, should probably be something like, the radius, right? Again, I get that just by looking at the data. Okay, the place where we need something, yes?
Is it correct to say that this is what, for example, signal regions at the LHC would be?
Very good. Yes, exactly. Yeah. So so doing something by hand is exactly what, like a cut-based analysis where I study the simulations of signal and background, and then I decide where to put my cuts. That's coming up with something by hand. Yes. Another example, yeah, I should give probably, thanks for reminding me, is, if I'm doing, say, boosted top tagging, then I know the top mass is a good feature. Right? I know physics, right? So I know the top mass, the W mass constraints. I know there's n sub jettiness that tells me how many prongs are inside the boosted top quark versus QCD. So I know all these high level features from physics, and I can use them to come up with cuts for this kind of decision boundary, right? Good. So that's the first thing that you probably should try when faced with this problem. Now, in the case where the data is too complex, or you need to get more out of the data than you can with high level features, maybe the data is 1,000 dimensional and I can't just make a plot like this anymore. Then I need more high powered methods. And so another, maybe I should give myself another page here. So another approach beyond that are something called decision trees. And there's something called boosting that makes them more powerful. And so BDTs are very, very commonly used in our field. And what those are and primarily for classification. And so that's like automating the choosing of cuts. So, it's a tree-like structure. So I might start off with some cut on like feature 1, x0 greater than 0. And if it passes or if it fails, then I'll do some other cut like x1 less than -1, or I'll do like x1 greater than 2, and pass, fail, etc. So that's roughly how a decision tree works. Okay, and it fits all these cut boundaries, these choices of the cuts to the data to maximize again some kind of log likelihood loss. Okay. So that's a very popular choice in high energy physics for machine learning classification. And the reason I guess it's very popular is that it is very fast and easy to train for small-ish number of inputs. So e.g. The number of X features are like 10 or so. Okay, so if I have like 10, if my space is say 10 dimensional, that's just a rough, figure of merit, a rough rule of thumb. If my space is 10 dimensional, so too high dimension, maybe to just make some plots and draw some cuts, and if I don't like have any physical intuition about it, then so 10 dimensional, then I can feed it to a BDT and get a pretty much like the optimal classifier that way. So the place where this breaks down, if my dimensionality of data is greater than, I don't know, like tens, then BDTs don't scale well. And you can see why, roughly, right? They have this tree-like structure. So, the number of branches or leaves on the tree are gonna kind of blow up as I have too many dimensions, too many, as my data has too many dimensions. Okay, so in that case, that's where we're led to the third class of fitting functions.
Sorry, I have one more question concerning that. Sure. Is it when you have a cut, let's say x0 greater than 0, is it then excluded that you reuse the variable x0 again later on, or could it?
No,
like 10 stages,
I don't think it's
10 stages
excluded.
later, you could again require that x0 if it passed a certain amount of other cuts, then it has to be whatever smaller than -10.
Yeah, so I mean, I think there's many flavors of decision trees, and I think, in general, it would not be wrong to come back. I mean, this way of setting it up where you kind of go through every dimension one at a time is just for illustration. I don't think that's what it actually does in general.
Okay,
and also
so
there could be
you could make it arbitrarily complicated even with a small number of features.
Yes, and also, this is like one branch of the tree. I can have another branch where I do something else to x naught, right?
Right.
I can concatenate as many of these things together as I want.
Okay.
And these are all parameters, what are called hyperparameters in general, that I have to set when I'm defining my fitting function.
So you still need some physical intuition into setting up a reasonable tree.
I wouldn't say you need physical intuition. I think you just need some kind of, in general, good machine learning algorithm. And there's no way to know in advance necessarily whether your algorithm is going to be good or not. It's kind of a black art. But a good one is not that sensitive to the choices of hyperparameters.
But for example, the ordering, if you first choose x0 and then x1 or so on, that should make a difference, shouldn't it?
Yeah, so don't take too literally that I have to do this in some order. Yeah, I think a real BDT is not gonna have a set order to it. Yeah. They're
Okay.
designed robustly enough that I never have to worry about the order. I just say, here are my 10 high-level features like jet mass and n subjettiness 3.2 and n subjettiness 2.1 and et cetera, et cetera. Here are my 10 features. Just go to town on it. And you don't have to ever see that. The ordering, it's doing something with the ordering that's not totally dumb. Yeah.
Okay, thank you.
Mm-hmm. Okay, great. So good. So if I have more than like 10-ish features, then BDTs are not going to be necessarily optimal, and that's where neural networks come into play. I think I should give myself another page for that. Okay. Neural networks. So these scale well to basically arbitrarily, well, okay, not arbitrarily, to higher dimensional data. Eventually, I guess you'll run out of memory on your computer. Okay, but they scale well to higher dimensional data in practice. That's what we observe empirically. And that's finally the subject of the lecture. But they are biologically, what is a neural network? It's biologically inspired. And you have your input, X, which you represent typically as a big vector. Represent as a big vector. And we represent the elements of that vector space as circles, typically when we draw these things. And then what the neural network function does is it feeds these inputs to hidden layers, what are called hidden layers. So each of these columns here is just to represent another vector. And each of these connections that I'm drawing here is just to represent essentially matrix multiplication. And then after some number of hidden layers, I will come to an output. So these are called hidden layers. And so what's going on here? So, oh, by the way, this is just one kind of neural network, but it's sort of the way we think about all of them. So this is called a dense neural network. You'll also hear it called a feed-forward neural network or fully connected neural network. Actually, sorry, you'll hear it called a fully connected neural network. And these are examples of feed-forward neural networks. It's called feed-forward because you only propagate the input through the function this way. It's only going this. There are other examples of neural networks that also have loops that are used for, say, natural language or sequence modeling. But the simpler kind, you just pass the information through this way, from input, this input to output. Okay, and so what's going on in each of these layers? You may have seen these diagrams before, and in case they look complicated, you can think of these diagrams as just graphical illustrations or graphical representations of matrix multiplication for, say, computer scientists that never took linear algebra. So if you know linear algebra, you don't need such a picture, and it's probably better just to think of what's happening in each hidden layer. So let's say each layer I'm going to represent with a vector x and a label j. Okay, so j equals 0 is the input, j equals 1 is the first hidden layer, etc. Okay, and so this is like x. Oh, okay, yeah. So x1 to x. There's going to be a proliferation of indices. I'm sorry. So in the hidden layer, in the jth hidden layer, there could be nh. It could be nh dimensional, right? That's a choice. I can put as many circles here as I want, and I can use different number of circles for each hidden layer. Okay, so this vector could have a different dimensionality for each hidden layer, right? And what these lines represent these are the weights, and they connect node I on this hidden layer with node J, like that. Or I guess I should use a different letter. Node A and node B. Right, so these weights are just matrices, right? So node A and node B, let's say. And so all that's happening is when I go from layer J to layer J plus 1, I'm multiplying by weight J. This is matrix multiplication. That's all I'm doing. Okay, and then it's also considered good idea to add something called a bias. So these are called biases. And yeah, these are the weights and these are the biases, although people often refer to them both together collectively as the weights. But yeah, these are the free parameters. Okay, so that's all that's happening when I go from layer to layer is I'm multiplying by the weight matrix. And so the weight matrix is, NHJ dimension by NHJ plus 1 dimensional. Maybe I don't need this index H. Okay. Okay, so this is NJ by NJ plus 1 dimensional matrix, right? And this bias is also a vector. Okay, so if this was all a neural network was, then it wouldn't be able to learn very much, right? Because it's just matrix multiplication all the way through. So there's one more ingredient that makes this, that's key to making this able to learn lots of non-trivial things. And that's the activation. So their nonlinearity. So there's one more ingredient, which is the nonlinear activation. So we have from J to J plus 1 layer, we have X J plus 1 is actually equal to some activation function. Sorry. WJ XJ plus V. And I guess you could have the activation function be different for every layer if you really wanted. All right, so what is this activation function? It's a source of nonlinearity, right? If I don't break up this linear multiplication, matrix multiplication structure, all I'm going to get is that this is related to this through one giant matrix multiplication, right? All the hidden layers don't even matter anymore. I could just subsume them all into one big matrix multiplication, right? What breaks this up and makes it able to learn nonlinear things is this layer by layer nonlinearity. And so for instance, popular choices for A of X that are biologically inspired include this function. Sorry, I didn't draw that very well. This is called the sigmoid function. This is X, this is A of X. So, oh gosh, I didn't write the sigmoid. I think the sigmoid function is this. So yeah, that should have the right properties. Yeah, so it goes from 0 to 1. That's a popular activation function. Another one is Tanch. Okay. These are biologically inspired by what people thought real life neurons are doing, right? If the input to the neuron is below a certain threshold, the neuron does not light up and transmit the information. And if the input is greater than some threshold, the neuron lights up and passes it along. That's why it's called an activation function, right? For technical reasons, people realize that these biologically inspired activation functions don't actually perform very well. They lead to something called the vanishing gradient problem, which I'm not sure I'll have time to explain in this course, but roughly speaking, the fact that these asymptote to constant values at plus and minus infinity lead to all sorts of technical problems when training these neural networks, because the information sort of saturates and there's no difference between X of 10 and X of 1,000 at that point. And so the sort of dynamic range of the data is sort of cut off. Okay, so in practice, the most commonly used activation function people realized looks like that. So this is called the rectified linear unit, and it's just F of X, or A of X equals X if X is greater than 0, and 0 if X is less than 0. So this is actually the most popular choice for activation function, and it sort of solves, at least in one direction, it solves the vanishing gradient problem. People worry about this other end causing vanishing gradients, and they'll do things like this, which is called leaky ReLU. They'll give it a little slope here, hoping that helps. But yeah, so that's this is the best practices activation function that's most commonly used. Okay. Any questions about that? People still with me?
Yes.
I would have a question.
Sure.
Is it not a problem that with the tangent superbolicus and the first?
Sorry, you're gonna have to speak louder.
So, can you hear me?
Yeah, it's kind of quiet, but yeah.
Is it not a problem that the last function, the ReLU function, is linear above 0 and the other functions are not?
Yeah, so that's exactly what you want, it turns out. You want it to be, you want it not to saturate. If it asymptotes like this, you get this vanishing gradient problem. If the gradient of this continues to, see, the gradient of this thing is going to go to 0, right? So if the gradient of this thing does not go to 0, then you're in better shape. Yeah. So that's what you want. Yeah, you don't want to squish the information. You don't want to squish the inputs to a range, like a fixed range between 0 and 1. Like the incoming input has range from -infinity to infinity. You'd like the output to have a similar unbounded range. Sort of the upshot of that. Yeah. Okay, there's one more thing that might be confusing to you, which is how does
you
this
still have to determine the W's, right?
Sorry, what?
You still have to determine the W's.
Oh yeah, we haven't talked about training this at all. We're just still defining the function.
Yeah, okay.
Let alone training it. Yeah. So I'll get to that. Well, we only have 5 minutes left. Okay, I'll get to that.
Yeah.
All right. So what else did I want to say about this? Oh yeah. So this may be confusing to you. I defined a function here, which is one-dimensional activation function. How does it act on a vector? Right. This is a vector, whereas this is a one-dimensional function. It looks like. So one sort of thing that may be confusing to non-computer scientists is it acts element-wise on the vector input. Okay, so that is maybe not a natural thing for us physicists to do, but that's what neural networks are doing. Okay, so this is a scalar function, scalar valued and scalar input function, which acts element-wise on the vector inputs. Okay. And yeah, what I won't have time to prove, but the reason, okay, so you put all this together. So the fully connected neural network with non-linear activation function. So this, you can then prove that with, so basically you can prove this satisfies, this has a valuable property, which is called the universal approximation theorem. And actually, so what is this universal approximation theorem? The statement is that the original statement, I don't have a reference, but the original statement is that an infinitely wide, so single layer neural network can approximate any, well, any, I'll put that in quotes, any function to arbitrary accuracy. Okay, so that was what was proven in the early days, is that just with a single layer neural network, but if you allow the number of hidden layers to become arbitrarily large, then in that limit, with a nonlinear activation function, it was originally proven for sigmoid activations and then later generalized to all these other ones. It can approximate any piecewise, continuous, smooth, blah, blah, blah function to arbitrary accuracy. That's the universal approximation theorem. And then later, this theorem was also generalized to, let's see, I think it was later generalized to if you hold fixed the number of hidden layers, the number of nodes on each hidden layer, but allow it to be arbitrarily deep, then it also approximates any function. So that's the universal approximation theorem. And the sketch of the proof, I'm not going to prove it, but the idea of the proof is that you show that the neural network can approximate this function. Okay, so the idea of the proof is you show that the neural network can approximate arbitrarily well a step function or this hat function, and then you can use the hat function to build up any arbitrarily smooth blah blah blah, any piecewise continuous blah 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 function. Okay, then build any function out of these. So this is the idea of the proof. Okay, so the universal approximation theorem is, at least it's believed to be, is why neural networks work. They are an incredibly, is part of why they are incredibly expressive family of fitting functions. Okay, it's only part of the reason why they work. The other part of the reason is the way we fit them to the data also helps. Okay, so but you have to have a function that can fit like any data to begin with, and neural networks appear to be such a class of functions. So with a sufficiently big neural network, you can fit anything. That's sort of the upshot of that.
Does this theorem tell you something more quantitative, like if you double the number of nodes, you get 2 times better statistics, or 4 times better statistics, or root 2 times better accuracy, or something like that? Some scaling?
I'm not sure. I mean, to be honest, I haven't gone through all the epsilons and deltas of the proof. It's that kind of proof, you know. It's like a real analysis type proof. So to be honest, I haven't gone through every detail myself. I'm not sure if they probably, like after the original universal approximation theorem, there were theses written on generalizations and things. So maybe somebody has proven convergence, like rates of convergence. You'd like to know, as I make the neural network bigger and bigger, like how quickly do I converge to the arbitrary function? So probably there are such statements. Whether I've ever seen them used, like in a practical setting, which is sort of my domain of knowledge, the answer is, I think, no. So I've never seen that applied any practical benefit. This doesn't mean that it couldn't be.
The theorem by itself, I should say, does not impress me that much. I mean, there's also Turing's theorem, right? That tells you any algorithm can be written on a Turing machine, but nobody works with Turing machines, right? For very good reasons. Yeah.
I think at least, so that's why I also qualify this like believed to be why neural networks work. So, it's not like, so this is highly idealized, right? We never deal with such neural networks, infinitely wide, single layer neural networks. We're dealing with, much smaller and deeper things. So, but, I think we're a lot closer to what this is, the idealized setting of this theorem than say a modern computer program is to a Turing machine. So I think that's why this still has a value for some kind of intuition. We're never that far from this this thing. Sort of in the
I would have
same. Go ahead. Yeah.
I would have interpreted as meaning that at least this tells me that it can work. And
Well, what is it though? I mean, this can work, right? Whether how close we are to this with something like this, where this is like 100 and not, you know, arbitrarily large, is the question. Right?
yeah, of course. But if
Yeah.
if it couldn't, even if the infinite case weren't possible to work,
Right,
then you'd be in real trouble.
Yeah. So it's like more like an existence proof almost.
Yes.
Right. Yeah. Which is also conceptually why I think that's why the Turing result is powerful. It says that, you know, it could work if you had a, yeah. It doesn't mean it's the only way to get it to work, but it's like an existence proof. Yeah. Okay. Any other thoughts or questions? Unfortunately, I'm up. Our 2 hours are done. I'm gonna have to recalibrate. I should know better. I always bite off more than I can chew. But yeah, so we'll have to get through a lot of stuff next lecture.
Well, it was also, there was questions and feedback, which was good.
No, that's good. Yeah.